So today's lecture is about what's called the central limit theorem, which is actually a pretty cool probability concept that follows on from last lecture and is kind of like a culmination of lots of concepts that we've learned up to this point, right? So actually I think this is a kind of a nice, after having had almost a whole semester of probability, we're going to talk about a whole bunch of concepts that all come together in this really neat theorem, okay? And so what we've been talking about this week is how does the sum and how does the average of a bunch of random variables behave, right? So basically last time we kind of looked at the mean and variance of a sum and an average of IID random variables, right? IID means that all these variables have the same distribution and they're all independent, okay? And the preview is that, remember that when I showed you the Plinko example from The Price is Right when we talked about the binomial distribution and we were looking at the probability of where those balls fell, you should remember that that kind of looked like a bell curve. It looked like a Gaussian distribution, right? And that's kind of interesting, right? So there's actually a very good reason why that's true, and that's the topic of today's lecture, okay? So basically, we talked about the sum and the average, and we also talked about the PDF, right? The PDF of a sum, right? Which remember, we didn't prove this. No, well, did we prove it? Yeah, we kind of proved it. Basically saying that if I take the same random variable and I add a bunch of those random variables together, that the PDF looks like the convolution of the PDF over and over again, right? And I kind of hinted last time at saying that, remember that if I convolve a pulse with a pulse, I get a triangle, right? And if I convolve a triangle with a pulse again, I get something that is a little bit smoother, right? And so it's not hard to imagine that in this case that if I kept on convolving the pulse with itself, you might believe me that it eventually turned into something that looks like a Gaussian, okay? But the cool thing is that it doesn't matter whether it's a pulse or a binomial or anything, it turns out that as I add up a whole bunch of the same random variable, eventually anything will look like a Gaussian, which is kind of surprising. So that's the preview of what we're going to talk about, okay? So the central limit theorem. And sometimes you'll see this abbreviated CLT. It basically talks about how the, talks about what happens to the PDF and CDF of the sample mean as n gets large, as we add or we average more and more of the same random variable. The surprising result, I'll even write down that it's a surprising result. No matter the distribution of xi of each of the random variables, in the limit, the distribution becomes Gaussian. Exclamation point, right? In a certain sense. And I'm going to describe for you exactly what sense that is, okay? Okay, so that's, and thankfully, I'm not going to prove that for you. I'm just going to kind of state what it means. The proof actually involves, remember last time I talked about how you could take the Fourier transform of a PDF, and that was called the characteristic function, and we all didn't want to do that because we left Fourier transforms over in signals, and I don't want to go through that right now, right? So the proof of this has to do with characteristic functions, and if you're interested, the proof is in the book. But for the moment, let's just talk about what the result is, okay? So last time, the setup was the following. We had a bunch of random variables that were independent and identically distributed. And we had the mean of these variables we're going to call mu, which was finite, and the variance sigma squared, which was also finite. So basically your run-of-the-mill, non-psycho random variable, okay? And we said, okay, suppose that I take the sum of n of these guys. So I could talk about the sum, and I could talk about the mean or the average, which is just 1 over n times the sum. So what we learned last time was that the expected value of the sum was going to be, well, I've got n of these guys added up, and so I should expect that the expected value is going to be n times mu. And kind of by the same token, then, the expected value of the mean should be 1 over n times this. So, you know, the expected value of the average is just the mean of whatever it is, right? That makes sense. And then the variance of the sum we showed was n times sigma squared. And then we showed that the variance of the mean was 1 over n times sigma squared. Okay? And just kind of going back to what we talked about last time, this is why if I add a whole bunch of random variables up, basically I get something that has the same expected value, but the variance gets smaller and smaller. I get a tighter and tighter distribution around the mean. Okay? So now what I'm going to do is I'm going to define a new random variable that's kind of like the average, but a little bit different. Okay? So let's consider a related random variable, and I'm going to call that Zn. Okay? So Zn is going to basically be the sum of the n random variables. I'm going to subtract off n times mu, and I'm going to divide by sigma times square root of n. So it's basically like the sum, just normalized in a different way, okay? I'm adding up the numbers, and then I'm subtracting off something, and I'm scaling them by something, okay? But it's more or less like a sum or an average, okay? So by our same reasoning as before, we can compute what is the expected value of this. Well, the expected value of this, I can see immediately, is going to be, you know, the expected value of this part is n mu, and I'm subtracting off n mu, so this has got to have an expected value of 0. Okay, regardless of the denominator. And the variance of this thing, the variance is basically going to be like 1 over this squared times the variance of this. And this itself was n sigma squared. So the variance of this thing is 1. Okay? So this is a specially constructed random variable so that at any point in time, or at any number of things I add up n, I've got a zero mean unit variance random variable. So in some sense, Zn is kind of like a well-behaved random variable, right? So no matter what n is, Z of n is zero mean unit variance. Okay? So, comments or questions so far? Now, just as a side note, you know, a lot of times, like if you're doing machine learning and computer vision, a lot of times this is a common thing to want to do to a measurement. You subtract off the mean and you divide by the thing so the variance is going to be equal to 1, right? That kind of makes your input, for example, to a machine learning classifier well-behaved, right? So this kind of thing is a good thing to do from a, you know, data processing perspective, okay? All right, so here is the punchline. Here is the central limit theorem. So now we're going to talk about this kind of specially normalized version, okay? So the central limit theorem says something about this Zn. It says that in the limit, so as I add more and more random variables to this average, this is like the CDF of this random variable, right? This is like the CDF of Zn, okay? And actually, maybe to make this a little bit less confusing, let me just call this U or something. This is just, you know, the CDF probability that this thing is less than some number turns out to be this function. Okay. So why is that interesting? Well, it's interesting because this is actually in here the CDF of a Gaussian, right? So this is the CDF of a Gaussian with mean 0 and variance 1. Right? Remember the equation for the PDF of a Gaussian. It was 1 over square root of 2 pi sigma, e to the minus 1 over 2 sigma squared, x minus mu squared. Right? So if I plug in sigma equals 1 and mu equals 0, I get this simpler looking PDF, right? So what am I saying? I'm saying that in the limit, as n goes to infinity, the CDF, right? This is, again, the CDF of my random variables added up equals this function here. This is kind of what we called this phi function is basically the CDF of kind of what we call the standard Gaussian with mean 0 and sigma equals to 1, right? That is, I have a Gaussian function like this. I draw the line at u, and this is the CDF of that function. And in fact, this is the same thing as 1 minus the q function, right? Remember all the q tables that we did before exam 1, right? That's like saying 1 minus the tail of the Gaussian, oops, starting at u, right? So let me just let sink in how exciting that is, right? That's basically saying that, you know, the more random variables of the same type I add up, the more they look like a Gaussian, right? And that's, you know, pretty surprising and also a little bit non-intuitive, right? That's like saying, imagine all the wacky PDFs of the source random variable that I could have, right? No, so, I mean, this is, again, emphasizing no matter the PDF of x, of xi, right? So for example, well, actually, maybe, you know, PDF is the same as CDF, right? So for example, suppose I had a coin flip, a Bernoulli random variable, right? This would be the CDF of a Bernoulli random variable. If I had a binomial random variable, it would look something like this, right? So this would be like the binomial CDF. If I had, you know, some sort of a, you know, weirdo, you know, CDF, like a continuous random variable, whatever it is, as long as it tops out at 1. Or, you know, some sort of a mixed, crazy thing, psycho PDF, right? So no matter what the input distribution is, as I add a whole bunch of them together, eventually I get the beautiful smooth bell curve, right? So that's pretty cool, right? And that is another piece of ammunition for why we care so much about the Gaussian distribution, right? Because certainly not every distribution in the world is Gaussian, but once I start adding up a whole bunch of non-Gaussian things, eventually they do become Gaussian. And that's why the Gaussian distribution is something that we care about so much, and also why we can model a lot of real-world phenomena as Gaussian, right? So you have to be a little bit careful because you know, the Gaussian is a continuous random variable, right? So certainly it's true that any continuous PDF, if I add a bunch of those, I get a nice continuous smooth Gaussian. I mean, if I had a bunch of coin flips, whenever I add up those things and normalize them, I still have a PMF, right? Meaning that I have impulse functions, not a smooth function. So kind of what happens in the, kind of for a continuous PDF, we get this Z of n, kind of looks exactly like what we want in the limit. For a discrete PMF, where we're adding up a bunch of things, kind of what the central limit theorem says, if we kind of look at it more carefully, is saying that, it's saying that if I choose a certain value and look at all the values underneath that, I get the same number that I get if I had a Gaussian. So kind of what you'd see if you had a discrete PMF might be something more like, a bunch of impulse functions, a PMF that if I were to kind of draw the line, it would look like a Gaussian, right? And also that you'd probably get something like this if you had some sort of a mixed half continuous, half discrete kind of thing. And so don't take my word for it. Let's look at what the computer has to say. So here's just a little applet that I found by Googling central limit theorem applet. And so here's an example of, you can say, okay, here's a bunch of random draws from a single uniform distribution, okay? So for a single instantiation, this is kind of like saying, where did the random variables I got lie? And I just make a histogram of them. And, it looks pretty uniform, right? This is one, random variable. Now suppose I take two uniform random variables and I add them together. All right, so now I'm incrementing this by 2. This is the distribution that I get when I add up those two things. And actually, this looks like the triangle we kind of talked about. Right? This is like the convolution of the box function with itself, right? And say I crank this up a little bit more, say I add 5 of them together. Now we're getting the bell curve. We got it pretty fast, right? And so, of course, if I made this even more, of course, it's not perfect, right? So you can see that, this is not a beautiful bell curve. If I did another version of this, I might get a different shape. But it's clearly Gaussian with the same mean and the same variance. And if I did some sort of like weirdo PDF, right? So here's, again, a pretty strange distribution. The weirder the distribution is, the more time it may take, the more draws and sums it may take for me to get to the Gaussian. So here, adding up 2 still looks pretty weirdo. And if I do 5, it's still not great. But if I crank it up to, say, 13, it's smoothing out that weirdness, right? Here's a, well, this is kind of dumb. This is a Gaussian to begin with, so I'm not really expecting that much to happen. I guess what this shows me is that, adding up Gaussians gives me Gaussians, so we knew that already. But here's an example kind of like saying, this is kind of like more like an exponential distribution, right? So here, again, and that's a little bit counterintuitive, right? You might think that if I kept up adding up exponential distributions, that I would get something that would still be kind of weighted towards the left-hand side. But if I add up a bunch of them, you can see that the mean starts to creep over to the middle. And the more I add up, the more centered that mean becomes. But it may take me a while, right? Now I'm something where it's looking like things are pretty well centered around the middle. So that's the big idea. So let's stop and ask, any questions or comments about this? And this is why, when you drop a zillion Plinko balls down the Price is Right board, you get something that looks like a Gaussian, right? Because what we're doing really is adding up a bunch of independent binomial random variables, right? That's exactly what's happening if I sent a million marbles down the Plinko board. So I encourage you to do the same Google and play with this yourself, but the system works, right? Pretty neat. And so, no one has any comments about this wonderful theorem? It's great. I guess you're all shocked by how great this theorem is. So what does this mean? This means that now, when we're dealing with the sum of a lot of random variables, we can really get away with only thinking about Gaussians, right? So the implication is that when n is big, we can use the central limit theorem to get good approximations of probabilities using our good old friend, the Q table, right? The Q table is the table of values of the Gaussian CDF, and that's all we need, okay? So let me write down a bunch of equivalent events, kind of, right? So, specifically, you may find yourself wanting to use one of these forms of the central limit theorem, right? So kind of what we said earlier was, if I normalized the Zn in a certain way, this is the kind of CDF of the Gaussian, which I said was basically 1 minus the tail of the Gaussian, okay? And let me rewrite what this Zn was, right? Because again, Zn is not always like the handiest way to talk about things, right? So if I were to renormalize this like this is the definition of Zn. And now I'm going to, what am I going to do? Well, I can make this something that's in terms of the mean, right? So I could say, okay, the probability that, well, first of all, let me write it like this. The probability that the sum is minus n mu is less than mu sigma square root of n, right? So I'm just going to write a whole bunch of things that this is equal to, right? Or if I wanted to divide this whole thing by n, it would be like saying mn minus mu less than or equal to mu sigma over square root of n. Oh, no, sorry, not mu. Oh, this is bad. U. I guess this is why I wanted to do z in the first place, right? So let me just, I'm writing the same thing, but let me just switch from u's to z's because I think that the mu and the u are too confusing. So let's write this as z instead. This is equal to phi of z. I'm just getting rid of the mu u confusion, right? So again, rewriting what I wrote before, nothing has changed. I only do this because you're going to see z in the book and in the notes and all that stuff. If I divide by n, I get this. Or a different way of thinking about this is like saying that, the probability, let's kind of write this as a picture, right? So the probability that the mean minus mu, so here's mu, and let's suppose that mn is here, right? So it's like saying, I'm talking about how far away mn is from mu. That's kind of like the one side, right? What I want to say as the other side is to say, okay, I could say the probability that I am more, or I'm sorry, less than mu from the mean, like this, is approximately 1 minus 2q of z, right? Let me draw that as a picture. That's kind of like saying, okay, I give you mn, and I want to know what's the probability that that number is within plus or minus this of the mean. And this number here is like z sigma square root of n, right? And I get that by taking 1 minus 2 times this tail, right? So you can see that you're starting to see problems that resemble the end of the last homework, right, where I was asking you about the probability that a minion's weight is in a certain range. Now we could solve that with the central limit theorem instead of solving it with this Chebyshev bound, right? That's what we're going to talk about in a second. So in some sense, this is kind of like, we're going to get into, if any of you have taken like a statistics class, you've heard of what's called a confidence interval. We're going to talk about that towards the end of this lecture also. All right, so let me pause and ask questions or comments. So I think that, when we're coming to talk about like working homework problems and solving problems on the final exam, these are the kinds of things that you want to have on your crib sheet, right, as a reminder for how to use the central limit theorem. Usually the standard format of these kinds of word problems is I give you a bunch of variables without, and I ask you for the third, right? So I might say, how many samples do I need to take to be 98% sure that I'm within 3 units of the mean, right? So in that case, I'm giving you the distance from the mean, the probability, and then I'm asking you to compute the number n, right? So that's the way that these problems tend to work, and I'm going to give you a whole bunch of problems right now along those lines, right? So let's do a couple examples that use this idea. So that will make it, I think, a little bit more clear. And so on this homework, you're going to get back to Q tables and being used to using them. Okay. So let's suppose that I've got a whole bunch of coin flips, right? Let's say that these are IID Bernoulli random variables with p equals 1/2, right? That's just a fair coin flip, okay? And that means that the mean of each of these guys is 1/2, and you can look it up in the book that the variance of this is also 1/2. The standard deviation is 1/2, the variance is 1/4, right? We can get that from just computing it directly. So now I can ask the question, basically, how close is the average of n of these numbers to 1/2, right? We kind of want to know, on the average, if I flip 1,000 coins, how close do I expect to be to 1/2, right? So let's suppose that I flip 1,000 coins, or 10,000 coins, and let's suppose that I set, I'm going to refer to this guy here. Let's suppose I set z equals 1. What does this statement mean? This says the probability that if I average 10,000 Bernoulli coin flips and I look at the distance to 1/2, and then let's suppose that I put in, okay, so then what is this z sigma squared of n? So z is equal to 1, sigma is equal to 1/2, square root of n is equal to 100. So that's like saying that the probability that I'm within 1/200th of 1/2, which is pretty close, that's like 0.005, right, is approximately, I'm going to say equals because we're all friends here, it's approximately 1 minus 2 times the Q function of this z value, right? This is the z that I chose. And so if I look in my Q table, Q of 1 is about 0.15, right? So that's equal to approximately 2 times 0.159, and that equals 0.682. So what is this telling me? This is like a case where I'm sorry, this is a little bit off the screen. This is a case where I'm kind of telling you everything, right? I'm plugging in all the numbers, right? So I already knew mu and sigma, and I told you n, and I told you z, and I just wanted to know, what does that statement tell me? It tells me that if I flip the coin 10,000 times, the probability of being within 0.005 of the true mean is 68%, which is pretty high, right? Now, if I were to make this z bigger, right? So if I were to say z equals 3, for example, then this number here, Q of 3, would get a lot smaller, and I'd be a lot more certain of being within that range of the mean, right? That would mean that I would be closer to 1/2, which means that I'd have a higher likelihood of that happening, right? And so I can kind of like use this mechanism to ask questions like the following. So let's suppose I wanted to know, for what value of n is the probability that I am within the same amount, this is the same 1/200ths, right? 0.005. Suppose I wanted that number to be at least 90%, at least 0.9, right? So how many flips would I need to have to ensure with 90% certainty that I would be that close to the mean, right? So now I'd have to do some reverse engineering, right? This would be like saying, okay, I need to have 1 minus 2q of some z value to be equal to 0.9, which means that q of that z value would need to be 0.05, right? So then I would need to look in my little table and say, okay, for what z value is q of z about 0.05? It's kind of somewhere in this range, right? Between 0.054 and 0.044, it's actually somewhere between 1.6 and 1.7, and it turns out, let's just split the difference and say that z is approximately 1.65, okay? So now I take this back to my statement and I say that means that, how do I get from here to n? So let's compare the information, right? So I'm telling you 1/200ths, and that has to be the same as this z sigma over square root of n. I know z, 1.65. I know sigma from the coin flip case is 1/2. I don't know square root of n, that's what I'm trying to find, right? So now I flip this around and I say, okay, that means the square root of n has to be equal to 200 times 1.65 times 1/2, and so this is about 165, and so that means that n has to be equal to 165 squared, which is about 27,000. Right? So this is like a classic example of jockeying this formula around, right? So again, let's recap what we learned. We learned in the first case that if I flip the coin 10,000 times, I would be within that tolerance of 1/2 with about 68% probability. And if I said, okay, but I want that to be 90%, then I would have to flip the coin 27,000 times instead of 10,000 times. So let me stop and ask, any questions about this? If you understand this example, you can solve any problem along these lines. Okay? Okay, so let's do a couple more examples. So let's go the other way, okay? So we can also do what are called confidence intervals, okay? So a slightly different take. Are what are called confidence intervals. So let's say that we want to stick with our original 10,000 samples. So say we want 10,000 samples. And, or say we have 10,000 samples. And we want to know the, what I would call confidence interval of the approximation of the sample mean to the true mean. Okay. And so let's suppose, for example, that I want to be, 10,000 samples, and I'm going to also now I'm going to keep the 90% confidence, right? So let's suppose that I say, for what region or for what interval can we be 90% confident. So again, you have to kind of work backwards and think about, okay, so what is known and what is not known, right? So that's like saying that, again, I want the probability of m 10,000 minus a half to be, you know, something here. I want that to be 90%, right? So if I want to say, okay, what is the 90% confidence interval? Now I have to compute what goes in this question mark box, right? So the question mark box is, again, the same z sigma over square root of n from before. And we learned that z for this guy, right, from the last example, was the same 1.65. And the sigma is 1/2, and the n is 10,000. So this equals, as it turns out, 0.00825. So what that means is that we have this statement. Or putting it a different way, that's like saying the probability that the mean is within kind of 1/2 plus or minus this number. This is about 0.9. We're 90% confident that the mean is within that interval, okay? So again, if we take it back to, you know, this was the original example where I was talking about 10,000 flips, right? Here I was saying that, you know, if I talk about 10,000 flips and I'm within 0.005, that is a tighter tolerance than this, right? So I can only be 68% confident that I'm in that interval. If I broaden the width of that interval a little bit, then I can be more confident. And if I made this even bigger, then I could be even more confident, right? So it's all kind of just like the same problem with different window dressing. So questions about this? Okay, let me do a more kind of minionish example referring to the homework, right? So the nice thing about this is that, you know, when n is big, the central limit theorem will give much better approximations of probability than any of these things that we talked about so far, like Markov, Chebyshev, etc. Right? Because as we talked about earlier, those bounds are generally very, very conservative, meaning that if I compute the true probability, it's going to be, you know, the Chebyshev bound is usually a lot further away from the true probability than I would expect, right? Because again, the Chebyshev thing came from extremely generic assumptions about the PDF. Whereas here, once n gets big, we know the PDF is virtually Gaussian. It's super close to Gaussian, right? So here's an example, which is, you know, you're going to see the relationship to the minions. Okay, so let's toss a fair die 20 times. You know, and we're going to add up all those dots on all those 20 flips. What is the probability that the sum of dots is in the range 60 to 80? Okay. All right. Well, let's first of all compute our kind of like mean and variance, right? So for each xi, for each of these guys, basically this is like a uniform distribution, a uniform PMF on the values 1 through 6, right? And we can recall from our table, from our memory, that the mean is going to be 1 plus 6 over 2, which is 3.5. And the variance is going to be 35 over 12, which is 2.92. And the sigma, if I take the square root of that, is going to be 1.71. So that just comes from the table, okay? So now let's talk about what would the Chebyshev approximation be. So the Chebyshev approximation, which is the same thing as last time what we called the weak law of large numbers, how would we work that kind of problem? Well, let's take this word problem and write it in terms of sums and means, okay? So this is like saying the probability that the sum of 20 random variables minus, you notice that I've always kind of structured this so that the interval is centered around the mean, right? So how many do I expect to get? I expect to get 20 times the mean, which is 70, right? So I'm saying the probability that I am within 10 of 70, right? That's the same as this statement here. Well, or a different way of thinking about this is saying the probability that the mean of the 20 guys is less than 10 over 20, which is a half, right? So this is the kind of thing that we could say from Chebyshev, or the weak law of large numbers, is 1 minus sigma squared over n, which is 20, times the epsilon squared, right? So this is going to be whatever it was, 2.92. So if I plug in all these numbers, what I'm going to get is, as it turns out, 5/12, which is 0.42. Just trust me on the math, okay? So this is what I get if I kind of used homework. I don't even know what homework we're on, 18? It's crazy. Okay, so if I use homework 18 logic, then I get this kind of probability. And you can see that this is not a very high probability, right? So it's like saying, well, yeah, it's at least 0.42. That doesn't seem like a lot, right? Now let's use the fact that after I do 20 of these guys, remember from my little applet that when I started adding up uniform distributions, only after about 5 or 6, things looked pretty Gaussian, right? So I'm pretty sure that after 20, everything should be super Gaussian, right? So let's see what the central limit theorem would say. So on the other hand, the central limit theorem would tell us, same setup, right? The probability that I am within 3.5 of the mean, I'm sorry, the problem that I'm within 0.5 of the mean, right? So now I would have to use my, go back and look at the key thing, right? Which is, I've got the mn, the mu is here, and now I have to, again, solve for what is z, right? This has got to be my z sigma over square root of n. So what is unknown? The unknown part is z, right? So this is going to be 1 minus 2q of z. So I have to solve for z. So here, this is like saying that z sigma over square root of n has to be equal to a half. This is z, which I don't know, sigma, which I know was 1.71, and then square root of n is square root of 20. So that means that I work this out, I get that z equals blah, 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 1.31. Okay, again, trust me on this. So then I compute what is 1 minus 2q of 1.31. I look to my table. I look over here and say, okay, 1.31, close enough to this, right? So it's like 1 minus 2 times, turns out to be 0.095, actually. And then the answer is 0.81. Okay? So let's review what happened, right? So if I didn't know anything about the PDF, and I just used the most minimal information possible, I would get something that says, okay, that probability is at least 0.42. If I use a central limit theorem, this is a very accurate probability, and I can see the actual probability is a lot higher, right? So this is a real underestimate of how much the true probability is. It's not wrong, it's just really low, okay? And this is a number that you can take to the bank, right? The bigger n is, the much more likely that the central limit theorem will give you the right number. All right, stop and ask. Good so far? All right, I got one more page of notes. So what more could there be to say? Okay, so let's see. First, let me just clear my page here. All right. So what I'm going to do is kind of tie this back to, confidence intervals and confidence levels, okay? So in estimation problems, a lot of times we don't know what the mean is, right? So kind of in real-world estimation problems, we often want to estimate, that's why they're called estimation problems, an unknown parameter by kind of, for example, averaging a bunch of samples. Okay? That is to say, suppose that I have a set of IID random variables, and I compute, the mean. And I'm just going to show you, this is like the same as MN, right? So this is nothing more than different notation for MN. Just that, sometimes in statistics, you'll see like this X bar instead of M, and it means the same thing, okay? So we know in the limit, right, that by the various laws of large numbers, we know that this average eventually converges to the mean, right? It converges to the expected value of one of these guys, right? But we kind of like to know how good that estimate is, right? How accurate it is for a given n. And this is usually posed as something like this. So let's let 1 minus alpha be some pretty high probability. For example, we may want this probability to be like 0.99. So that means that alpha is a small number, okay, just as a setup. So what I want to do is I want to find a lower bound and an upper bound such that the probability that the true mean is within this region is equal to 1 minus alpha. Again, let me kind of write this in words, right? This is like saying the probability that the true mean is in this region, and that these u's and l's are functions of x and n, right? That is, suppose I'm trying to estimate the average. I don't usually, say I'm flipping a bunch of coin, or flipping a coin, I don't know whether it's fair or not, right? I'm trying to estimate what is the p, what is the Bernoulli parameter for that coin. I can't assume it's a half. I want to observe it by flipping the coin 1,000,000 times. Now I see what the average the average value is, and I want to know how confident can I be that p is in a certain region, right? So that is we kind of know that the true mean is in a determined range with high probability right? And this is called the 1 minus alpha % confidence interval. Okay. So here, 1 minus alpha is called the confidence level. And this bracketed range here is called the confidence interval. So again, this is the same setup and the same idea as before, okay? So let me do, again, working through the machinery, okay? So here's the setup. The setup, again, is that each of these guys is IID. And let's suppose, for example, that I don't know mu, right? So unknown mu. And for this to work for the moment, let's suppose that I know the variance. And we'll talk for a second about, it's kind of weird that I would know the variance but not the mean. Sometimes it happens, but let's suppose that's the setup, okay? So what we know is that from the central limit theorem that 1 minus 2 times this Q function is this probability. Why is that? This is just a different way of writing this over here, right? Because this is, this is the same thing as this. So let's kind of write this out a little bit more. I'm just going to move things around. Minus z sigma squared of n, xn minus n mu. Then I'm going to add the n mu on both sides. Actually, no. I mean, this is true, but this is not what I want. Sorry. What I want is this. I'm going to keep the mu in the middle, and I'm going to write it like this. What did I do here? Oh, you know what? Sorry. I knew I was confused here. Let's just rewrite this. Throw it away. All right. Suppose I'm not even going to include that in the notes. It's not even worth including in the PDF. IID, unknown mu. I knew sometimes when you're writing this down, you know you're writing something wrong, but you can't really put your finger on why it's wrong. And I just figured out. Okay, so let's rewrite this again. Apologies. So looking at this, right? So here, the setup is that I'm looking at this range. Wow, lots of things are wrong with that previous page. Let's all just first agree that this is true, right? All I'm doing here is I'm taking this final equation here and I am dividing through by sigma over square root of n, right? So all I'm doing is I'm moving this part over to the denominator of this. I'm happy with that now. Okay, and now I'm going to make this a little bit more clean. Right, this is the same z sigma square root of n that we always have. Okay, and now I'm going to keep the mu in the middle, and I'm going to move the xn over. And a little bit of arithmetic should convince you that this is true. Okay? So what is this saying? This is saying that this interval contains mu with probability whatever 1 minus 2q of z is. Okay, so the setup, right, is that I've got a bunch of random variables, I compute their average, and then that's what this xn bar is. And now I want to know, okay, so I computed this average, can you give me a plus or minus range so I can be pretty confident that the mean is within that number I computed plus or minus something, right? That's how I'm going to estimate this unknown parameter, which is the mean, okay? So if we set alpha, which is kind of like our confidence level, and we compute z so that 2qz equals alpha, okay, then this number here is going to be equal to this probability. So all I'm doing is I'm substituting in what I just did here. Mu is in x of n plus or minus this z value. And let's call this z value alpha over 2, because I'm computing the z, so q of z equals alpha over 2. So it's whatever that z value turns out to be. Right, so this is some interval around the sample mean, and I can be pretty sure with confidence 1 minus alpha that I'm inside there, right? So let me do an example to, again, crank this through, okay? So example. Let's suppose that my random variables have unknown mean, and I happen to know that the variance is equal to 1, right? So my mean is not known, my sigma is equal to 1, okay? And now I measure x 100 times. And what do I find? I find out that the average x that I got of these 100 times was 5.25. Okay, that's like a number that I got from actually doing experiments, right? Find the 95% confidence interval on the mean. Okay? So the setup is that I did 100 measurements, I looked at my average, I came up with 5.25, right? So now I know that my true mean is somewhere around 5.25. How close is it? This is what we're going to do. We're going to compute it, right? So I want to be 95% sure of giving you an interval that contains the mean, okay? So here, my n is 100. I did 100 experiments. My sigma is equal to 1. My alpha is 0.05, right? That's equal to 1 minus the 95%. And now I need to find z such that q of z is equal to this number over 2. We're going to call that this. So now I have to go back to my table, and I have to find what number z is basically pretty close to 0.02. And I can see it's going to be, you know, right around here, right? This is pretty close to 0.02. And you can actually look in, so this is a table that I'm going to give you on the exam. So here, you can see that if I look at the 0.25, I get that 1.96, right? This is really high-class lecturing. So I can already tell it's, you know, close to this. I know it's pretty close to 2, and you can look that up in the table. So instead of having to eyeball it, you can actually get these values from a table. This z sub 0.025 I'm getting from the table is 1.96 from a table. It's kind of like an inverse Q table, right? It's kind of like a reverse lookup. Okay, so now what can I do? If I use that information, that's like saying that I've got all the pieces I need to do this. That's like saying the probability that, you know, so the confidence interval the 95% confidence interval for the mean is thus, I take the number that I computed from my actual experiments, 5.25, plus or minus this number, 1.96, times this number, 1, over this number, 100. And so that's basically 5.25 plus or minus 0.196. And so that means that my mean is within basically 5.05, 5.45, right? I can be 95% confident that if I did this experiment, that I'm close to that value. Yes? Should the 100 have a square root? Okay, oh, yes, right, because I only divide this by 10, right? Sorry, yeah, good catch. Okay, yes?
What situation would you ever know the variance for sure, but not the mean?
Good question. So, you know, why would I ever know the variance but not the mean? Okay, so that leads me into my final paragraph on my page of notes. So if we basically don't know sigma, and n is large, then we can still get confidence intervals on the mean. So we can still estimate confidence intervals on the mean using some additional stuff. And maybe you've heard of the t-distribution, the student's t-distribution. Okay, so I'm not going to teach that in this class. This kind of is something that if you took like Mao instead of probability, you'd be doing this t-distribution stuff, right? So again, it's just a different table lookup kind of problem, right? So instead of a Q table, you're using kind of a more generic table, okay? But yes, if you didn't know sigma, you could use the t-distribution table to help you with that. Or kind of if you do the other way, if you said, you know, or if we knew sigma, and, or I'm sorry, if we knew the mean and want to find confidence intervals on the variance, we can use lookup tables based on the chi-squared distribution. So all these kinds of problems are just variations on a lookup table, right? So in this class, you only have to care about the Q-table version, which means that you don't know the mean and you do know the variance. However, like you asked, there are lots and lots of variations on this theme where I know this and not the other, or I don't know either of these things, and all it implies is there's a different table to use, right? And that gets more into statistics and t-tests and p-values and stuff like that. We're not going to talk about that in this class. That's more about like data analysis than it is about probability. Okay, but that hopefully answers your question. If you want to know more about this stuff, there is a chunk of the book that talks about different things to use in different situations. I think that's section 8.4 of the book. All right, comments or questions? Okay, that's it. Have a good week.